Okay, grade 10s, in this lesson, what we're going to do is we're going to revisit geometry. In particular, we're going to be looking at the midpoint theorem. It's a brand new theorem, and it's really a cool theorem. So let's explore this a little bit. We're going to be using the geometry that we did in previous lessons, so be aware of that. But let's explore what is the midpoint theorem. It says the line joining the midpoints of two sides of a triangle is parallel to the third side and equal to half the length of the third side. So what this theorem is saying is if you've got a triangle, what it says is that you're given that AD is equal to DB, okay, and AE is equal to EC. And if you're given that DE is the line segment joining the midpoints of these two sides, then, so if this holds true, then what we can prove is that DE is parallel to BC, so these are parallel. And what's more interesting, if that DE has a length of x units, BC is double that length. In other words, BC or DE would be half the length of BC. So this is called the midpoint theorem. Okay, the line joining the midpoints of two sides of a triangle is parallel to the third side and is equal to half the length of the third side. Okay, now I'm going to prove this theorem, and it's really cool to prove it. And what I'm going to do is I'm going to do a little construction. So this is how I'm going to approach it. I'm going to write here construct. Okay, so we're going to construct line segment FC, and we're going to make it parallel to AB. So this is a construction here, that line segment AB is parallel to FC. Okay, that's a construction. And DE is produced to F, and they meet there. Okay, now, how are we going to prove then that DE? So this is what we have to prove. We've got to prove the following. We want to prove very simply that DE is parallel to BC, and we want to prove that DE is a half of BC. So there's two things to prove here. Now I want you to focus on these two triangles here. Okay, and I want to show you how easy this is to prove. The first thing, what do you notice? Do you notice that AE is equal to EC? Alright, you've got that there. Also, look at this here. Very interesting. You've got angle A is equal to angle C2 because of the parallel lines, alternate angles. And likewise, F is equal to D because of the alternate angles there. So we've got a situation of congruency here. Side, angle, angle. Okay, now let's prove the triangle's congruent, and then I'm just going to show you exactly what happens after this. Very cool. So what we've got is we've got in triangle, let's take triangle ADE, so that's this top triangle here, ADE, and in triangle CFE. So that's the two shaded triangles there. What do we know? Okay, well the first thing that we know is that AE is equal to EC. That is a pair of given sides there. Okay, there it is. AE is equal to EC. We've got two sides equal there. Then, what also emerges is that D1 is equal to F. Alternate angles equal. Look at that. So D1 is equal to F. The alternate angles equal. And likewise, we can say, for number C, we can say that angle A is equal to C2 once again. Alternate angles equal. There we go. A is equal to C2, alternate angles equal. And therefore the triangles are congruent. So we can say therefore triangle ADE is congruent to triangle CFE. Side, angle, angle. What a pleasure. Okay, now if the triangles are congruent, automatically we can then conclude that if you see this AD, the length of AD is equal to FC. So we can mark those off there. So we can say, therefore, AD is equal to FC. Okay, but what else do we know? What do we know about AD? AD is equal to DB. and that is given to us. Look at that carefully. If you have a look at this, we've got AD is equal to FC proved via congruency, but now we've got AD is equal to DB. This piece here is equal to that piece. Now, if that's the case, we've got all of these three sides being equal, or lengths being equal. So this means that out of this, we can say that DB is equal to FC. So look at this. So we can say, well, if AD is FC and AD is DB, the conclusion, therefore, is that FC must itself equal DB. And that's critical, that FC is equal to DB. FC is equal to DB. But what do you notice too? That the lines are parallel. This was the construction. FC is parallel to AB. So we know that immediately we can also conclude, we can say that also FC is parallel to DB. There's a critical fact that FC is parallel to DB. And if that's the case, then what we can say is if we've got in this quadrilateral DBCF, okay, look at that, in DBCF, if we've got one pair of opposite sides being equal and parallel, then it must be a parallelogram. So we can say that, therefore, we can say that BC, let's write there, BCFD is a palm, is a parallelogram, and the reason being one pair of opposite sides equal and parallel. So there it is. So we've got here BCFD is a parallelogram, or DB, any way that you like. Doesn't really matter how you express that, but it's a parallelogram. And therefore, we can immediately conclude that because it's a parallelogram, that therefore DE must be parallel to BC. Because if it's a parallelogram, the opposite sides are parallel. Therefore, we can say that DE is parallel to BC. That's the opposite sides of a parallelogram. Isn't that cool? Okay. And then, but now, once we've got that, we can say also that therefore, now watch this, that DF is equal to BC for the same reason. Because of the opposite sides of a parallelogram. Look at this, that DF, the whole of DF, is equal to the length of BC. Okay. There, that, which is pretty cool. Okay, and what also do we know? We know also that, look at this, that DE is equal to EF. That's from congruency. Now look, we've got the whole of DF, this whole length DF equaling BC. We've got DE being equal to EF. So the result follows. Watch this. So we can say, alright, now let's just go to black again. We can say we've got, but, now watch this, but DE is equal to EF. That's from the triangles being congruent. And therefore, and we've also got, so we've got DF equal to BC, DE equals EF. Look at that again. DF is BC, DF is BC, DE is equal to EF. Therefore, DE must be half the length of BC. Because think about it, if that whole of DF was, say, 20, then DE would be 10 and EF would be 10. You see, but BC would be 20. Do you see that there? So, in other words, DE is half of BC, and there we've got it there. So we can say, therefore, DE is a half of BC, and we've proved the midpoint theorem. Okay, so in essence, what the midpoint theorem is saying, if you look at this carefully, it says that if, in this triangle, if you've got AD is equal to DB, and at the same time, you've got AE is equal to EC, then the conclusion is that DE is parallel to BC. So if AD is DB and AE is equal to EC, then these two lines are parallel. Okay, the other, and then also DE is a half BC. You could also say that BC is twice DE if you like as well. That's also true. Or another version of this, if you've got, if AD is equal to DB and if DE is parallel to BC, then what we can conclude is that AE is equal to EC. So in other words, look at this. If you've got AD is equal to DB, you've got the two lines parallel. The conclusion is that those two will be equal. And this is all referred to as the midpoint theorem.